Okay, this is the Algebra 1 lesson on section 3.6. We're going to look at solving compound inequalities. So let's start with our warm-up. Again, pause it if you have not done the warm-up yet. Okay, so I'm going to move this 3 over, and then I'm going to get x is less than, if I take 10 minus 3, x is less than or equal to 7. I'm going to move this 3 over first. I'm going to rewrite it over here. So that gives me 20 is less than negative 2x. Now I need to divide by negative 2. If I divide by a negative number, I need to flip the sign, so I get negative 10 is greater than x. Okay, move my 1 over. 4x is less than 24. Divide by 4. X is less than or equal to 6. On my graph, I've got 6, 7, 5. I'm going to do a closed circle at 6, and it says x is less than or equal to, so it's this way. Okay, I'm going to move my 3 over, so I'm going to have negative 3 is greater than or equal to 3x. I'm going to divide both sides by 3. Negative 3 divided by 3 is negative 1 is greater than or equal to x. So negative 1, 0, negative 2. And do a closed circle at negative 1. It says x is less than. Again, I like to read it with the variable first. X is less than or equal to negative 1. I would suggest you guys watching pretty much all of this video today just because a lot of it is new. So we're going to look at solving some compound inequalities with one variable and then graphing the solution sets of those inequalities. You'll hear the words compound inequality, intersection, and union used. Okay, so the inequalities that we've seen so far are simple inequalities. When two simple inequalities are combined into one statement by the words and or, the result is called a compound inequality. So for example, here's a compound inequality. X is greater than 2 and x is less than 6. And the way that we write it merged together is that x is greater than 2 and less than 6. Okay. Here's another one. So they're two different inequalities, but they combine them together to make a new one. So a way of reading this is all the real numbers greater than or equal to 2 and less than or equal to 6. When we do the or, we can't combine them. We just keep them as two separate inequalities. So for example, all the real numbers less than 2 or greater than 6. And then finally this last one, all the real numbers less than or equal to 2 or greater than or equal to 6. They like to use the all real numbers versus saying the variable. Okay, so let's try one. We've got the pH level of a popular shampoo must be between 6 and 6.5 inclusive. That's going to be important, the inclusive. Write a compound inequality to show the pH levels of this shampoo and then graph the solution. Okay, they want us to use P as our variable. So I always start by writing my P. And my first thing says that it's between 6 and 6.5. So that means P has to be less than 6.5, okay? Less than 6.5. However, the word inclusive means we're including those numbers. And then on the other end, it says it needs to be bigger than 6. So 6 is over here, and P needs to be bigger than or equal to 6. So to graph this, I'm going to draw closed circles at both of my endpoints. And then it's everything in between them, okay? So just to like visually kind of show you what's going on in the diagram here, we've got an oval with A that has some integers that are x is less than 10, so like -4, -1, those are all less than 10. And then on the B side, it's everything greater than 0, 12, 25, 15, things that are bigger than 0. In the middle, they're showing you what overlaps. So these things satisfy 1, 2, 7, 9. They satisfy both inequalities, that anything less than 10 and anything bigger than 0. Okay? All right, we can graph the solutions of a compound inequality involving and by using the idea of an overlapping region. That just means what's in common with the two. So the overlapping region is called the intersection, and it just shows the numbers of the solutions of both inequalities. So for example, let's say I had the inequality x is less than 10 and greater than 0. So this is my compound inequality. Well, the two separate ways of writing them are here, and they're showing you that if we graph the first one and then graph the second, the result is just the two combined where they intersect down at the bottom, okay? All right, so let's try this. We're going to solve the compound inequality and then graph it. All right, so we've got three sections. We need to get x by itself. So that means I need to get rid of this 1 right here, and to get rid of it, the inverse operation is to subtract 1. If I subtract 1 from this section, I have to do it to all parts of the inequality. So make sure that you are aware of that. So then I'm going to get negative 6 is less than x, because this cancels, which is less than 2 minus 1 is 1. Okay, so my two endpoints are 1 and negative 6. So down at 1, because it's a less than sign, I'm going to do an open circle at 1. And then at negative 6, it's also going to be an open circle. And it says that x is less than 1, but it's everything greater than negative 6. So it's everything in between. Okay. All right, so here's another one. Again, we've got to find x, and we want to isolate it. So first we need to get rid of the 1 by doing the inverse operation, which is adding, and we're going to do it to all the parts. So 9 is less than 3x, which is less than or equal to 12. Now, the inverse operation of 3 times x is to divide by 3, and we have to do that to all the parts. So 3 is less than x, which is less than or equal to 4. Okay, now we're going to graph it. So I'm going to put 3. Actually, let's graph it on the next slide. I forgot they show you on the next slide. Okay, so together the inequality was 3 is less than x, which is less than or equal to 4. So the two separate inequalities are 3 is less than x, and then x is less than or equal to 4. So let's graph them separately. So I'm going to put, this is my 0, 1, 2, 3. Sorry, that was the bell, guys. Negative 1. So we want to make sure that the number lines line up with all 3 here. Okay, so x is greater than 3. So that means I'm going to have an open circle at 3. Or sorry, yeah, x is greater than 3. And it's everything to the right. Now the second one, x is less than or equal to 4. I'm going to do a closed one at 4. And it's everything x is less than. So everything this way. Now the intersection points is everything right here. So I've got an open circle at 3, closed circle at 4. And then it's where they overlap. Okay, and you don't have to do the two inequalities, graph them separate, but I'm just showing you where that's coming from in case you're confused by it. Okay, so now we're going to look at compound inequalities that use the word or in them. So in the diagram here, we've got, again, our x is less than 0 or x is greater than 10, and we can't combine these inequalities, okay, because they don't overlap anywhere. So this is why we're using the or in these examples. So there's no overlapping. So again, we would graph them separately, okay, but the combined regions are called the union, and it's not where they overlap. So for example, x is less than 0. They show you right here, x is less than 0, and then x is greater than 10. My final way that I would write this is that I would just do the two separate inequalities on the line, okay? So let me show you an example. Okay, so 8 plus t is greater than or equal to 7, or 8 plus t is less than 2. We need to isolate our t, so we need to work out each one separately. So to get rid of the 8 on this one, I'm going to have t is greater than or equal to negative 1. This one I also have to subtract 8. That's just because it's the same on that side. It's not always going to be the same. So t is less than, I'm going to have negative 6. Okay, so now we're going to graph them separately. Okay, but let's do the first one. T is greater than or equal to negative 1. So that means at negative 1, I'm going to do a closed circle. Okay, and it says that t is greater than or equal to negative 1. So that means it's everything to the right. Okay, my second one, t is less than 6. So I'm going to do an open circle at 6, and then t is less than. So that's everything to the left. So do you see how there's no overlapping on this? Okay, it's just what they call the union. All right, so here's another one. 4x is less than or equal to 20, or 3x is greater than 21. Let's solve each one individually. So this first one, I'm going to divide both sides by 4. So x is less than or equal to 5. And then let's solve this one. I'm going to divide both sides by 3. X is greater than 7. Okay, so I've got two inequalities. Now we're going to graph them separately. X is less than or equal to 5. I'm going to do a solid circle at 5, and it says x is less than or equal. Okay, so it's everything to the left. And then x is greater than 7. We're going to do an open circle at 7, and then it's everything to the right, since it's everything is greater than. So there is your compound inequality for that one on a graph. Okay, to be a solution of an and compound inequality, the solution has to make, sorry, another bell. The solution has to make both parts of the compound inequality true. If none of the numbers are solutions to both inequalities, then that inequality has no solutions. And then for it to be a solution of an or inequality, it has to make at least one part of the inequality true. It may make both parts true. So just keep that in mind. Okay, that's important. To be a solution of an or, it has to be true for one of the sections. It doesn't have to be true for both, but it can. Okay, again, the and, it has to be true for both of them. All right, so we're going to write the compound inequality for what's shown. Now, since there's nothing overlapping here, we can tell that this is going to be an or one. So for my first one, I've got x is everything to the left of a -8, so x is less than or equal, since it's a solid, to -8, or x is everything is bigger than 0, so it's everything greater than 0, and you're done. Okay, let's do one with an and. So I always like to start by writing my variable in the middle, okay? And I know that for this first part, x has to be less than 5, okay? So I've got 5 over here, and x has to be less than 5. And for my other side, x has to be everything bigger than -2, so I write -2, and I know x, I have to face it toward the x because it's bigger. So you are done with that, okay? So again, just make sure you understand the and versus the or. The big thing to point out is that to be a solution of an and compound inequality, if it tells you to check if it's a solution, it has to make both parts of it true. If one of the parts isn't true, then there's no solution. For the or one, as long as it satisfies one part of it, then it can be true. Okay? And that is all.